Welcome back to ECE 320A. What we want to do today is something that you maybe haven't seen before, and that is actually performing ladder analysis on circuits. And you don't have to go out and purchase a ladder, but this is designed to work on circuits that can either be in the time domain via differential equations or in the frequency domain, but it works on circuits that look like ladders, or if you want to think about it, it really is sort of these mesh circuits that are laid out in this horizontal fashion, and it looks sort of like you could step up the rungs of the ladder as you might be working your way from right to left, where in our circuit, maybe I should just show you the circuit. Here is our circuit. If you use your imagination, hopefully you can see that these vertical elements could be looking like the rungs on a ladder, and we want to now work our way from right to left, from the output variable V sub C across to the input or the supply V of T, and do that in a step-by-step fashion so that we're not just writing mesh equations and then inverting a matrix or doing some kind of last minute or at the end computation, and we don't even know, or we can't really follow the analysis that has occurred in going or deriving the end result. And that's what we want to do here. We want to perform some ladder analysis. Again, you can do it in the time domain, which is what we will do today. We will be working in the time domain with differential equations, but you could, once we get further into the material, we will be starting, or we could start with a circuit in a S-domain form, and we could apply this same technique or strategy in the frequency domain if we wanted to. Here again, the ladder analysis is getting its name because the circuit looks somewhat like a ladder on its side, and the process allows us to see the analysis as we progress step by step through or up the rungs of the ladder, and we can follow our analysis, and we don't at the end say, oh, I must have made an algebra mistake or in the computation. Now we can sort of follow the analysis as we proceed, and it makes sense at each step what we are actually obtaining as a result. And the approach will be to start at the output variable and work our way across the ladder towards the input. And here is the example circuit that we will use to help illustrate that. And as we go, I'm going to keep scrolling back and introducing more notation so that we can see as we move through this approach how it builds and we work our way across the ladder from right to left. So our goal really is to find a differential equation that relates the output voltage V sub C of t, and I've tried to color code this, to the input V of t. So we want to end up with a differential equation. In this case, you can probably anticipate the order of that differential equation. That's going to depend on the number of energy storage elements that we have. We have two energy storage elements, so you should be anticipating a second order differential equation that's connecting V sub C and its derivatives to the applied voltage supply V of t. That's what we want to have happen. And we will do that by trying to write all of the equations as we move up the ladder from right to left as linear combinations of the output voltage V sub C of t and its derivatives. That's the idea, that we want to now start writing these equations. For example, now we might say, oh, we could also identify an I sub C of t, and we know what that is in terms of the output voltage. We could then say, oh, our next step might be to identify this current, which we might call I sub R sub 1 of t. And we can do that because we know that at this particular node A, that has the same voltage dropped across R1 as it does C. So let's do this process in a step-by-step fashion to try to come up with this second-order differential equation that connects the output variable V sub C to the input source V of t. As I've already hinted, the first step is to connect this output variable V sub C to the current flowing through that capacitor. And we can do that by invoking ice. So step one is to just use our current voltage relationship of a capacitor to derive a connection between the capacitor's current, I sub C of t, and its voltage, which is now I sub C is equal to C dV sub C of t dt. And I may actually collapse that dV sub C of t just to make it a little bit cleaner or more compact and just say V sub C prime as the derivative of the output. So we have the output V sub C, that's the voltage across the capacitor. We now have an equation for the current through that capacitor in terms of the output voltage V sub C and or some linear combination of its derivatives. And in fact, the current I sub C is a scaled version of the derivative of that output, and the scaling is the capacitor C. We now have I sub C of t written in terms of V sub C. We can also write I sub R sub 1 of t in terms of V sub C because V sub C or R1 and C are in parallel, which now by just using Ohm's law, we can see that I sub R sub 1 of t is now equal to V sub C of t over R sub 1. Now what do we do? Again, we're trying to work our way by solving for voltages and currents until we get back to the very first voltage on the left, which is our supply. So now we have two currents leaving node A. There's only three branches going into node A. So we can actually hopefully see that we can now express the current through R sub 2 that we're labeling I sub R sub 2 in terms of I sub R sub 1 and I sub C by simply performing KCL at node A. So step 3 will actually be KCL at A, and that now says that I sub R sub 2 of t is now equal to I sub C of t plus I sub R sub 1 of t. And as we said, we want to rewrite that in terms of the output voltage and its derivatives or linear combinations of those, so that now I sub R sub 2 of t is I sub C, but that's C V sub C prime of t plus I sub R1, and that's V sub C of t over R sub 1. And so we've met our obligation. We now have I sub R sub 2 also expressed as some linear combination of the output voltage V sub C and its derivatives. And we have that same for I sub R sub 1 and the same for I sub C. So now we can go a little bit further. Again, we're writing voltages and currents in terms of V sub C and its derivatives. The next thing that we can do is we can work our way back to the next node by noting that this voltage drop can be written in terms of I sub R sub 2. So step 4 in this process of working our way from right to left, step 4 is another application of Ohm's law. And if we didn't have a resistor, we might have to implement ICE or Eli. But here we can say that V sub R sub 2 of t is simply r sub 2 I sub r sub 2 of t. That's Ohm's law. Or, now that we have I sub r sub 2 in terms of v sub c and its derivatives, we can now likewise write v sub r sub 2 in terms of v sub c and its derivatives, or r sub 2 is now going to be multiplying I sub r sub 2, which is c v sub c prime of t plus v sub c of t over r sub 1. That's step 4. What's step 5? Well, now, before we can maybe even obtain this current through r sub 3, we might need to know what this voltage is across r sub 3. But we can find that voltage. That's now just the sum. If we just do this KVL, we now have v sub r sub 3 in terms of v sub r sub 2, which we've already found, and v sub c. Step 5 then is going to be KVL. And here KVL is minus v sub r sub 3 of t plus v sub r sub 2 of t plus v sub c of t equaling 0. And that now allows us to write v sub r sub 3 of t is equal to, putting that on, or isolating that on one side of the equal sign, that's now v sub r sub 2 of t plus v sub c of t, and v sub r sub 2 we just found, that's r2c v sub c prime of t plus r sub 2 over r sub 1 v sub c of t plus v sub c of t. Collecting like terms, we then have v sub r sub 3 of t is a derivative term scaled by r sub 2c, and the v sub c term that's scaled by 1 plus r sub 2 over r sub 1. We now have v sub r sub 3, and I think you can get the idea. Now we can solve for I sub r sub 3, and then we will be able to write a KCL equation at B. That will allow us then to find I sub L of t, and once we have I sub L of t, we can use Eli to find V sub L, and once we have V sub L, then we can find an equation that's true by just writing KVL around this blue highlighted region. So let's just write those steps down rather quickly now that we have the pattern. Step 5 was KVL. That gave us V sub r sub 3. We're up to step 6. And step 6 is going to just be a straightforward application of Ohm's law to obtain the current through resistor R sub 3, I sub R sub 3 of t, and you can see that you feel comfortable or confident in the equations that are resulting from this ladder analysis. There's not that big of a jump in any particular computation, and now I sub R sub 3 of t becomes R sub 3, 1 over R sub 3 scaling the result from step 5, or we now have R sub 2 c over R sub 3 v sub c prime of t plus 1 over R sub 3 plus R sub 2 over R sub 1 R sub 3 v sub c of t. And as we hinted before, step 7 is going to be a KCL at node B so that we can now rewrite or find an equation for I sub L. I sub L is just I sub R sub 3 of t plus I sub R sub 2 of t. And we have all of those written in terms of v sub c and its derivatives. Or I sub L of t is now I sub R sub 3. That was just the line above. So we now have R sub 2c over R sub 3 v sub c prime of t plus 1 over R sub 3 plus R sub 2 over R sub 1 R sub 3 v sub c of t plus I sub R sub 2, which better be c v sub c prime of t plus v sub c of t over R sub 1. Again, collecting all of these common terms, and that's not hard, but do you see that if we just ended up with a inversion that we had to perform, then we might not be able to track down all of these terms and the algebra related to them. We have 1 plus R sub 2 over R sub 3, all scaling by C, and those now weight the derivative of the output voltage V sub C. And now we have three terms, 1 over R1 plus 1 over R sub 3 plus R sub 2 over R sub 1 R sub 3 that scale V sub C. That now gives us the current through that inductor, and we can relate the voltage and current on an inductor using Eli. So that will be step 8. Step 8 is Eli, which now says that V sub L of t is L I sub L prime of t. And now we'll just have to differentiate what we just found and scale it all by L. And doing that now allows us to write the following. Now we have V sub L of t is equal to L times, it's not a very pretty curly brace, so let me change that. All times C times 1 plus R sub 2 over R sub 3. We need to differentiate V sub C one more time. So there's our double derivative, which we were expecting a second order derivative in V sub C, plus 1 over R1 plus 1 over R sub 3 plus R sub 2 over R sub 1 times R sub 3 V sub C prime of t, and close the curly brace. Whew. Well, we're almost there. We're back basically to where we wanted to end up, which was at the terminal of our voltage supply, V of t. We now simply have to write a KVL equation around that blue highlighted region. We have minus V if we start at the lower left-hand corner, plus V sub L, plus, well, let's just stop it at plus V sub R sub 3, since we have that in terms of, so now we're sort of doing a shortcut. We could sort of say, let's just do it this way. Let's just write a KVL around there because we already have V sub R sub 3 in terms of all of the remaining variables, and they're all in terms of V sub C. So step 9, is that where we're at? Step 9 is now really a trivial KVL. And the trivial nature of that now says that we have minus V plus V sub L of t plus V sub R sub 3 of t is equal to 0. Isolating V of t on one side of the equality now says that V of t is equal to the sum of V sub L of t plus V sub R sub 3 of t. And that's not hard now to write all of that down. Now V of t is equal to V sub L, which is LC times 1 plus R sub 2 over R sub 3 V sub C double prime of t plus L, I'm just pushing the L through where I needed to, 1 over R1 plus 1 over R sub 3 plus R sub 2 over R1 R3 times V sub C prime of t. And now we need to add in V sub R sub 3, which is R sub 2 C V sub C prime of t plus 1 plus R sub 2 over R sub 1 V sub C of t. And I hope that you can then see that we now have our second order differential equation connecting or relating our voltage supply V of t to a linear combination of V sub C prime, and V sub C double prime. Let me now just collect all of those coefficients into some betas, and now I hope you can believe that we have a V of t equal to beta sub 2 V sub C double prime plus a beta 1 V sub C prime plus a beta 0 V sub C of t. And that's really the ladder analysis. If we wanted to carry it just a little bit further by leading into our next material, which is inverse Laplace transforming, let's now go into the Laplace setting and see if we can solve this. This is now a second order differential equation. We can solve that second order differential equation by jumping into the frequency domain, doing our manipulation in the frequency domain, and then inverse Laplace transforming to get us back into the time domain. Let's now try to follow those steps. First, let's Laplace transform. Doing that, the left is just the Laplace transform of little v of t, which is capital V of s. Then we have beta 2, and let's go ahead and keep track of all of the initial conditions. We now have s squared v sub c of s minus s v sub c of 0 minus v sub c prime of 0 minus, and those are the time domain value of the capacitor voltage at 0 minus and the time domain value of its derivative at 0 minus, plus beta 1 times s v sub c of s minus v sub c of 0 minus, plus beta 0 v sub c of s. And we can combine all of those. We have some initial condition terms. We have the Laplace transform of the output voltage, V sub C. Let's combine all of those together. Or V of S is now going to be beta 2 S squared plus beta 1 S plus beta 0 all times V sub C of S. And now we have our initial condition terms to keep track of. We have our polynomial in S that scales the Laplace transform of the variable that we want to find in the time domain, which is the output voltage of our capacitor. We have its Laplace transform, but we also have terms that are associated with the initial conditions, which is now a minus beta sub 2 V sub C prime of 0 minus a beta sub 2s plus a beta 1, where I'm accounting for the minus sign in total, V sub C of 0 minus. We now have our voltage V of S, that's the supply voltage, written in terms of a polynomial NS times the Laplace transform of the output voltage V sub C, and then we have some initial condition terms associated with the capacitor voltage and its derivatives. We're trying to find the output voltage across the capacitor as a function of time. Let's go ahead and define this polynomial in S. It's a second order polynomial because we had a second order differential equation that has the betas. Remember, those betas were because of or associated with these linear combination of terms of L's, R's, and C's from our differential equation. If we now solve this equation at the top in terms of V sub C or for V sub C of S, we can divide that characteristic polynomial through on both terms or both sets of terms. I'm now referring to V of S as one term and the initial condition pieces as another term or a second term. We can then identify those particular pieces. We now have V sub C of S, our Laplace transform of the capacitor voltage, as a linear combination in the frequency domain of a term that involves the forcing function, its Laplace transform, capital V of S, and that's divided by the characteristic polynomial. That characteristic polynomial will give us the poles, and that gives us the behavior of our system. And then we will have a second Laplace transform piece that is associated with the initial condition terms that involve the output voltage's initial value and its derivative's initial value. Now, what we will subsequently learn is how to inverse Laplace transform, move from the frequency domain back into the time domain, so that now we would find capital V sub C of S if we inverse Laplace transform that, which we're indicating by this script del raised to the minus 1 power. That's now the inverse Laplace transform of the forcing term and the inverse Laplace transform of this initial condition termed piece. We then can see that the output voltage of that RLC circuit will have two pieces, one due to the forcing function, little v of t initially, and the other due to the initial conditions on that particular circuit. And that's then where we want to end up at the other side of this stepping back and forth between going from the time domain to the frequency domain. We want to be able to, once we've jumped into the frequency domain and done the analysis, done the solving, we can then go back into the time domain by the inverse Laplace transform, and that is what we will be learning in subsequent lessons.